Hello and welcome to another lecture of ECE 108. This lecture is all about going through and figuring out which method we want to use to try to prove something. So in general, we have a lot of methods that we can now use to prove something, and kind of a big question and something that students struggle with is how do you decide what method to pick and what are the relative merits of different methods for different problems. Now, generally speaking, this is a very hard thing to quantify since there's a lot of problems in math and a lot of problems in math aren't currently solved, right? So if we could answer what method would work in every single case, then we'd either basically be able to prove everything or prove that you can't prove various expressions that haven't yet been proven. And there's actually a theorem saying that you can't guarantee that you can do that within mathematics. Gödel's theorems, we'll maybe talk about that at one point within this class. So let's just kind of talk about some general methods that generally will work just by going through a bunch of examples where we have a statement that may or may not be true, and we just kind of stumble upon our possible options for trying to prove it. Okay, so let's talk about how we can try to pick which method to use and just some pro tips and some common fallacies that students make. Okay, prove or disprove this statement. If this x squared minus x, plus x plus 2 is less than 0, then x is in here or x is in here. So let's just examine this, okay? So here, I'll just put it over here. So this is the thing that I want to try to prove or disprove. So out of our methods, one of them kind of obviously won't work here. Induction. So we have kind of shown how you can generalize induction so that it can work on R, but no, we're not doing that. So let's just kind of think through our options. So the first option that I usually consider when looking at something like this is, hey, could I do this via a direct proof? So let's look at that real quick. So if I wanted to do this via a direct proof, what would I need to do, and could I do this via direct proof? So a good idea of things to ask yourself when doing these type problems is, what if I tried this method, as opposed to saying, okay, I'm going to do this method, it's going to work, and forcing yourself to stay in that method. So just kind of pro tip number one, so to speak, would be to look at a question and keep an open mind about different things you could do, right? Just because you could do it doesn't mean you should do it.
Yeah, but your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should.
So let's just think here. If I wanted to do a direct proof, then my starting point would need to be that this statement here, that x squared minus x squared plus x plus 2, that this has to be less than or equal to 0. And then I would need to show that if this is the case, then I could do some manipulations and come to the conclusion that x would either have to be in this interval here or the other interval. Okay, so doing this, the real question in this context is, can I actually do manipulations here to tweak this inequality here into two possible ranges for x? So in particular, can I solve this expression? So if this were, say, like a fifth order difference equation, if this was a fifth degree polynomial or something like that, then you might not be able to solve it. So this method might not be the best idea in general. But if this is just a quadratic, then yeah, I can analyze this inequality, split it up, and try to figure out what values of x could solve it by finding the roots. So in this case, a direct proof does work, so let's do it. So here, if this is going to be the case, so if, and I'll just copy paste here. Okay, so if this is the case, then what can I say? Well, here I know that I can factor this polynomial, right? So here I can say if this is true, then I know that 0 has to be greater than or equal to, well, how does this thing factor? So if you just look at it for a little bit, you could see, like, hey, if I pull out a negative, then I could just write this as x minus 2 and x plus 1. right? So here, that times that gives me -2. With negative gives me the 2. When I FOIL all this out, I get a -1, where the negative gets a 1, and negative x squared. Okay, so from here, if I want this inequality to be true, then I know, well, from here, this thing tells me, this implies that it must be the case that either this thing is negative and this thing is positive, or this thing is positive and that thing is negative. So just kind of writing this out, I could say something like, thus, we must have that either, well, in one case, I would need my minus x minus 2. This thing I could say, hey, if that's less than or equal to 0, and on the other case, my x plus 1 is greater than or equal to 0. In this case, that would be negative. Or, and put a line to separate this out, my other case would be where this first one is going to be greater than or equal to 0. And at the same time, this second one has to be less than or equal to 0. Okay, these are the only situations where these thing, like this thing, can be less than or equal to 0. Right? I can do this nice split up using the properties that a positive times a positive is a positive, and a negative times a negative is negative or positive. And if I have switched positive times negative, I get negative. Right? So now what I can do is I can analyze both of these cases, and hopefully, if it turns out that this is true or this is true, then I'm done. But if I get an extra statement, then I can find a counterexample that would break this. For instance, if in this case, if it so turns out that in this case x has to be less than or equal to, say, 0, then I could say, hey, 0 would work as a counterexample. It doesn't, because if I plug in 0, I do get something, like I don't get a counterexample, right? Because the premise isn't true. Okay, so from here, now I just want to do some algebra here and here to simplify this out. Okay, so if this thing is true, then I can solve this for x. So if I multiply by the negative, it'll flip the inequality, then I can add 2. So from here, this first one tells me that x has to be greater than or equal to 2, again, flipping inequality and adding 2, and at the same time, x has to be greater than or equal to -1. So out of these two, this is the most constrictive. So I can say, thus, in this case, I need it to be the case that x is greater than or equal to 2. Okay, so this gives me my first little bit up here. So this is kind of a good sign that this would be true. So now if I analyze this case and I get this thing here, or something more restrictive than this, then I'm good. If I get something that's a little bit weaker than this, then I could potentially find a counterexample. Okay, so let's go through here. So from here, again, I flip the sign and add the 2. So here, I'm going to get that x has to be less than or equal to 2. And in here, I have x has to be less than or equal to -1. So out of these two, this time, this one's the most restrictive. So I can just write, thus, x has to be less than or equal to -1. This is the same thing as this case up here. So I can thus put, thus the statement holds. Okay, so in this case, a direct proof works. So I'm just going to take this work, clean it up, and throw it into the slides. And then let's just look at doing, say, contradiction or a proof by the contrapositive to see if those would work, right? This was an easy enough proof, so might as well use it. But sometimes one of the other methods could work or give you something better. And in the worst case scenario, by examining those extra cases, we can learn about when not to use a case, just in case they don't work out, which TLDR, they don't actually work out. Okay, now that we have a nice clean state here, let's just think about the case where I try to do contradiction. Okay, so this is a symbol for contradiction, so I'm just going to use it instead of writing out contradiction. So in the case of contradiction, what would I need to do? So I would first need to assume that this is true. So I'd have to say, let this thing be true. And then I would assume for the sake of contradiction that the other bit is not true. And so I can say assume. So instead of for the sake of contradiction, for the sake of contradiction. There we go. And what would I assume? I would assume that this thing. I would assume not that x is in this interval, 2 minus 1, or this interval, right? And do feel free to use symbols instead of words. It can make things a little bit cleaner. So if I want to negate this, this is the same thing as just saying that x is in the open interval from minus 1 to 2. Okay? So this is what I'd want to use and find a contradiction. So I'd want to say that if x is an arbitrary real number, and this is true and this is true, then I get a contradiction. Now, this you might want to just say is, hey, so we could say, why not just let x be some particular number? So pick x to be, say, 0. Okay, so why not just let x be 0 and plug it in to see if it works? Well, if you let x be 0 and plug it into here, it does work, but that's actually not proving this, because the thing that we want to prove is that this is true for all x. So why can't we just pick something like this? Well, we actually need to find a contradiction for all x and r that satisfy both of these properties. Thus, we need a contradiction for all x in that interval. So then this begs the question, how do I go about doing this? Well, in this case, it turns out that it's not actually very useful to try to do this, but in other cases, it does work. So if I want to try to get a contradiction for all x in the interval, what I need to do is I need to assume that x would be bounded, oops, I don't want that one, would be bounded below by minus 1 and above by 2. Okay, so then what I want to do is I'd want to use this information to get bounds on these other terms here, and ultimately the goal would be to try to bound this whole thing by 0 in this case. So for instance, if x is between minus 1 and 2, what does that tell me about x squared? Well, if I square any of the values over here between negative 1 and 0, that would be between 0 and 1. So here I get that this would be bounded below by 0, which this is true just because if I square any number, it's positive. But this bit here is bounded above by 1 when I square it. This bit's bounded above by 4. So here the only thing I can really state is that this is bounded between 0 and 4. Okay, so that gives me bounds for x squared, but I really wanted a bound for this negative x squared. So from here, I could then simplify by noting that this directly would imply that my negative x squared would be bounded above by 0 and below by minus 4. Okay, so here I really ultimately on this thing, the thing that I want is to bound this above by 0. So this is the bound that I really care about. The other one I may or may not care about. Now, on the other hand, I have this x plus 2, and I can easily get a bound for it, right? So again, if I just take this and add 2 to it, this will imply that my x plus 2 would be bounded above and below by some stuff. In particular, what would it be bounded by? Well, here, if I add 2, I get a 1, and I get a 4. Okay, so fixing one little error here real quick. I had equal signs here that where I shouldn't have. So from here, I somehow need to use this information here along with this information here, potentially with that little bit, to somehow show that this whole thing, when I add them together, is bounded by 0. Well, here's kind of where the problem comes in with doing this. I mean, you can get it to work, but these have signs going the opposite directions. So this is just going to be kind of messy to get a contradiction. It's possible to do, it's just going to be kind of messy, right? And the issue is really coming because I can't use this single thing here. I have to find a contradiction for every value of x. So this method, it's not super viable in this case, but in other cases, it can be quite nice. Okay, so that just leaves doing the contrapositive. So let's just clean up real quick and put on our contrapositive hats. So the first thing we need to do is think of what the contrapositive would be. So in this case, the contrapositive, or I'll just do CP for contrapositive, what would this be? Well, it'd be not this, so the negation of this would be, just to do work on the side real quick, this is the type of thing that you could say immediately, but it would be that x is not in this set, and x is not in this set, right? Just using De Morgan's laws here. So from here, this, since x is a real number, we know immediately that the negation would be x is in this complementary set here. Okay, so if x is in this set, then we need to show that this inequality does not hold. So the negation of that inequality would be this thing here. And for the sign, we just want greater than, because we need to exclude the equal to case here. Okay, so if I wanted to do a contrapositive, I need to show, hey, if x is here, then this is true. So again, this can be quite useful in some cases, more so when you just have a single bound, but just kind of chasing it out a little bit. Here, we're really saying that if x is bounded between 1 and 2, then if I plug x into this expression, that whole expression is bounded. So while it's not super fruitful to try it this way for the exact same reason why the contradiction wasn't a particularly nice method here, you can still do the same type steps, like negative x squared. What would that be bounded by based off of this? Well, it's definitely bigger than 0 because of, yeah. Actually, here you'd have a equal to 0 in this case, because this could be 0, right? And it would have to be bounded below by -4. So you'd get this, which is a little bit wonky. But yeah, so for these type problems, contrapositive and contradiction can be very useful, but really only when these bounds that you get here kind of have a nice synergy with this thing here. So keep in mind that these can be useful, and you definitely will want to try these methods. It just so works out that they're not super nice for this question. Okay, so just kind of done examining them. Here's the one proof that I presented earlier, and this would be the way that I would go here. So let's look at another question real quick. So prove or disprove. For all x and r, if x squared isn't equal to 4, then either x is not equal to 2 and x is not equal to 4. So ignore the either there. So this is the thing I want to prove, and we have options to prove this, right? So induction, well, x is r, so let's not use induction. I usually try to rule out induction first, because if induction is problematic, then it's usually pretty easy to throw that one out as an option. Okay, so for here, let's first look at a potential direct proof. So if I was doing a direct proof, I would need to start with the assumption that x squared is not equal to 4, okay? And using this, I would then need to show that this statement, that x is not equal to 2 and x is not equal to -2. I need to show that this thing would be true here. Okay, so this is, like, you can do this, but it's not the cleanest thing to do, right? My starting point is that this thing is a true statement, so I don't really want to kind of solve things like this. I'm used to solving things like that. That would be nice, right? So I really want the negations here to have a nice concrete equation to start with. Now you can, right? You can say, hey, if x squared isn't equal to 4, then I conclude that x isn't going to be equal to plus or minus 2, because these plus or minus 2 are the only things that solve x squared is equal to 4. But you're kind of speaking in negatives there. So while this does work, I personally wouldn't try to do this thing here, just because it takes a little bit of kind of contrary thinking here. Okay? You can do it, and you can make a proof like that work. I just wouldn't suggest doing it. So let's think of our other methods. So we have contradiction, or we have contrapositive. So let's try contradiction first, just to see what it would look like. So if I tried a proof by contradiction, what would that be? Well, so here I would let x be some real number such that this thing here is true. So I still have a negation. I would have this thing here. And then I would assume and assume for the sake of contradiction. And what would I assume here? Well, I would assume that x is not equal to 2 and x is not equal to minus 2. I would assume this thing is a false statement. Okay? Well, this thing being a false statement is the same thing as saying x is equal to either positive 2 or negative 2. Okay? So here I'm really wanting to assume this statement here to prove this. Okay, so from here I would basically do my proof like, hey, if x is equal, well, via cases, so case 1, if x is equal to 2, then this implies x squared is equal to 4. That's a contradiction. And then I would say, hey, since x squared is equal to 4, it contradicts this, therefore x can't be 2. And then I would assume the other bit, if x is equal to minus 2, same thing. It gives me the same contradiction here. So I could do this. It kind of has those two little awkward cases there. And generally speaking, I think this is the nice way of doing it. So let's just show how to clean up this work to make something a little bit cleaner. Okay, so undoing all that and wiping out the rest manually. Okay, so here, just remember I'm using this as an acronym for the sake of contradiction. So if you ask a question on that, I'm going to assume you didn't watch the video and send you to the video. Just heads up. Okay, so we're going to assume for the sake of contradiction that x is equal to 2 or x is equal to minus 2. Okay, so then we'll do two cases. Case 1, so I'd say, hey, if x is equal to 2, then I can conclude what? Well, x squared is equal to 4, and this is a contradiction of our assumption that x squared is not equal to 4. Okay, and then I just chase out my case 2. Hey, if x is not equal to minus 2, then x squared again is equal to 4, and I can just copy this over. Okay, so here, these are the only possible cases, right, for my assumption here. Thus, I can conclude that by contradiction, so thus by contradiction, and feel free to use this symbol for contradiction everywhere. I can usually a longer line there, but thus by contradiction, the theorem holds, or the statement is true. Kind of your choice there. Okay, so that's all there is for this one. This is kind of a nice, precise proof, so I will use this one and see you in a bit. Okay, so now just for completion, let's try doing the contrapositive to see what we get in that case. So for the contrapositive, what would the contrapositive be? Negation of this implies that. So this would be if x is equal to 2 or x is equal to minus 2, again, De Morgan's law, then x squared is equal to 4. Okay, so this one, again, is pretty clear. You just plug them in, and you don't have to deal with the contradiction, so you could argue this is a little bit nicer, but you would just do like a case 1. If x is equal to 2, then you can say, oh, multiplying by x gives me x squared is equal to 4, done. Or in the other case, if x is equal to minus 2, same idea, square both sides and just get x squared is equal to 4, or just square the x if you want. And then you could just do thus the contrapositive is true. So the statement is true. Okay, and do make sure if you do a proof by contrapositive, you make a statement like that, right? So if I just called this whole thing 1, so 1 is true. Okay, a little bit messy, especially with my handwriting on this little tablet I'm still getting used to, but yeah, that's the basic idea here. Contrapositive works even nicer, but it's your choice if you want contradiction or contrapositive here. They're basically the same difficulty level. Okay, so just throwing those two in via contradiction and via contrapositive, and it really is just your choice which one of these two you want to pick. Okay, let's look at one more example here. If x in z is divisible by 3, then x cannot be written in this form for any n in z. Okay, so here we have stuff happening with z, so a priori you might think this could be our potential chance to do some induction, right? Because integers. But it turns out that this isn't actually a very good induction type thing, purely because over here I'm starting with arbitrary thing, z, but I'm not doing all z's, right? I'm only doing the z's that are divisible by 3. So you could, if you wanted, you could do induction on n, where you're considering things of the form 3n, right? Because if you know it's divisible by 3, it has to look like that for some value of n. So here you could do induction this way, but you would have to make the argument before you start your inductive argument that if for these things that you are considering here, this is sufficient to work with. Okay? But then on each bit, it's still kind of awkward-ish, but yeah, let's stop beating about around the bush and actually just do it. Okay, so if I wanted to do this by induction, what would I have to do? Well, we would first say if x in z is divisible by 3, so I'll just put is such that 3 divides x, so this is notation to mean is divisible by 3, then from here we can conclude that there exists an n in z such that x is equal to 3n. Okay, so now what I would want to do, so after I have this set up, that's before I get to the inductive bit, is I'd say we proceed by induction on n, where p of n is the statement that 3n cannot be written in the form of 3n plus 1. Okay, and I swear I didn't do it. I'm in my room. I have nothing to do with the sirens outside. Anyways, so here's where I'm going to do my induction, but in particular, you note here I want to do things from z. So this n that I have from this statement here is also an arbitrary z. So I'd have to do the two inductive type things, right? So I'd have like my case 1, case 2. So I really should have done that outside here, but I'll digress from now because I'm not going to carry this proof all the way to the end. Anyways, so yeah. So from here, what I'd have to do is check P0. Yeah, if this is 0, then 0 is a number divisible by 3, and 0 can't be written in this form because it can't. It's kind of obvious, right? So here, just to be a bit formal, I would say if n is equal to 0, then 3n is equal to 0, and this can't be written in this form. And here I want to use k instead of n just to keep it a little bit different because, or as, if 0 is equal to 3k plus 1, this has a unique solution. K is equal to negative 1/3, and this thing is not in the integers, right? So since that's not in the integers, I have a proof by contradiction here that I've kind of done at this point, where this thing can't be written of that form to prove the p sub 0. Okay, and then I'd basically do the p sub k, where k is greater than or equal to 0. And again, I'm just being sloppy here because I'm doing kind of scratch work, because this isn't the ideal method here. But in this case, you would say, hey, if I have something that's 3 of the form 3k, where k is here, and if this thing can't be written as that, then if I replace k with plus 1, you do some rearranging to get the same thing. It's kind of messy. It's awful because you have to do all of this stuff. Then you either have to do the thing where you do p of k implies p of negative k that I mentioned in the previous lecture, or you have to go repeat all of this for the negative values where you subtract 1. So it does work. It's just not ideal. And generally speaking, when you see something where you start with an arbitrary integer of a particular type of form, so like in this case with this extra statement here, induction's usually not the best way to go. It does work, but yeah. Okay, so if induction isn't the method that we want to use, what do we want to use? Well, what about a direct proof here? Well, if I have a direct proof, let's just kind of write it in symbols to see what we need to do. So for a direct proof, I would need to say, hey, if there exists an n and z, actually I don't want to use n because I use n over here. So if there exists a k and z, such that x is equal to 3k, then I need to say there does not exist a n and z such that my x is equal to 3n plus 1. Okay, so we can do this, but generally showing non-existence is kind of messy. It's not as easy as showing existence, but let's just show how this would work. Okay, so this is my assumption, and I want to show that there exists this thing with this property here. Well, if I wanted to show this directly, or sorry, there doesn't exist this thing. Well, if I wanted to show this directly, I need to show that this, the existence of this implies that I can't do this thing. Well, the easiest way to show that you can't do something is to assume you can and then get a contradiction, and that's not a direct proof. So there really is no like pure direct proof way of doing this other than to kind of sneaking contradiction in there somewhere. So let's throw this away as an attempt, just because proving something does not exist is hard. And let's just think of other ways I can go about it via contradiction for now. Actually, we'll do contrapositive first. So from contrapositive. So if I'm doing contrapositive, I need to first think, like, what is the contrapositive? Well, it's the opposite of this implies the opposite of my hypothesis. So from here, x cannot be written in this form means x can be written in this form. So here we'd say if x can be equal to 3n plus 1 for some n and z. So if this thing is true, then I would need to show that that implies that x cannot be divisible by 3. So cleaning that up and then using some notation here, we could say 3 does not divide x. Okay, again, so this 3 does not divide x, if I unpack this, this is really saying, again, there does not exist a k and z such that x is equal to 3k. So again, I need to prove a non-existence. So that's not necessarily again, the same issue with doing a direct proof, right? So from here, I'd really want to do contradiction on the contrapositive, which sometimes is actually a really quick, easy way of doing some problems. But just because you're doing double negation, it's a good idea to try to avoid it if possible. Okay, so that leaves either giving up and crying that there is no proof to it, or trying to do contrapositive. Contradiction, at least from what we have. So if we try to do a contradiction, what would we do? We would say let x, b, and z be such that to be clear, there exists a k and z where x is equal to 3k. Okay, and from here, I would then assume, for the sake of contradiction, that, well, the negation of this. The negation of that would be x is equal to 3n plus 1 for some n and z. Okay, so my goal is to get a contradiction. Well, here, since I've switched all of my does not exist type things into existence theorems, I have concrete equations that I can work with, namely these two things here. So how do I go about doing this? Well, I would say, hey, if this is true and this is true, then 3 times k has to equal 3n plus 1 for some integers n and k. Okay, so from here, let's just do some simplifications. So I could subtract off the 3n and write this as 3k minus n is equal to 1. And finally, k minus n is equal to 1/3. So at this point, you could argue that this is the contradiction if you wanted, right? Because these are integers. This is saying the difference between two integers is not an integer, so that's not a thing. So you could do this, or you could go one step further if you wanted and say k is n plus 1/3. Okay, so this is a contradiction because the difference of integers is not a rational number, or is an integer, or an integer isn't equal to an integer plus a rational number, right? Like, you can't simplify this out. Okay, so from here, this is a contradiction, so you can conclude that the theorem is true. So thus, the statement holds. Okay, so this is quick, clean, to the point, and this is why when doing the previous proof by induction, this is why I wasn't super concrete and clean when writing everything out, just because I knew this proof existed and it's much quicker. So if, for instance, you got stuck on saying, hey, I can do induction here, not necessarily that you should do induction here, but if you got stuck into that mindset, then you could spend hours or half an hour at a minimum trying to chase out all those details, making sure everything's correct, doing all that case analysis, having those sub-contradiction proofs sitting there, whereas this proof is just sitting here happy and ready to be used, but you didn't stumble across it because you got stuck in your ways of I'm wanting to make this proof work. So generally speaking, if I give you a question, something like this, then just take a step back and check out your options and see what is the best way to go about solving that question. Okay, that's just a very strong hint that I have all throughout. Okay, so I was originally debating throwing in another inductive type question here, but we did a few of them in the last couple of lectures. They're kind of obvious to see when induction would work. And we're already at like the 30-some minute mark. So I'm not going to include that extra question here, and we'll just jump to ending the lecture just to save you some time to keep the videos on the shorter end. Okay, so here's kind of this proof written out, being a proof by contradiction. And let's go to our assigned reading stuff. So for assigned reading, I want you to think about a particular problem. So think about how you might prove this statement here. Okay, so for any integer n greater than or equal to 1, I'm going to define the sequence a sub k that will depend on n by, first, a sub 1 is equal to n, so the first value of the thing in the sequence is 1, or sorry, n, and if n's 1, you get the first one. And then we're going to use this recurrence relation here to define the other terms of the sequence. So let's just see what happens. If the previous number is even, then I divide it by 2, and that's my next one. And if it's odd, I multiply it by 3 and add 1 to it. Okay, so prove that for all n, there is this index m greater than or equal to 1, such that a sub m is equal to 1. So all this is saying is, hey, this is for any given starting value of n, this thing generates a sequence. And this is saying, prove that for all of these sequences, eventually you get the number 1 appearing in that sequence. So let's just look at a few examples of what these look like. So just in table form, here for various values of n, so if n is 1, I start at 1, so basically I'm done, the proof's done there, but let's just see how this works. If it's 1, 1's an odd number, so I take 3 times 1 plus 1 to get 4. 4 is now even, so I divide by 2 to get 2. 2's even, so I get another 1. And now that I have a 1, I do the 3n plus, or 3a sub k plus 1 to get 4, and this pattern will just oscillate forever. Now if I start out at 2, literally I'm just going to go 2, 1, 4, 2, 1, 4, 2, 1, just from the same reason why I was having this pattern over here, right? if I start out at 3, I get something different, right? 3 is odd, so 3 times 3 is 9 plus 1, so a2 is 10. Now 10's even, so I divide it by 2 to get 5. 5 is odd, so I multiply it by 3, add 1 to it to get 16. Now 16 is a power of 2, right? So when I divide it by 2, I get 8, 4, 2, and eventually to 1. So here you can kind of notice that every time I have a power of 2, I very quickly go to 1, right? So that might be something useful if you try to prove this thing. So you can kind of notice patterns like that, and kind of just noticing that, you could make a lemma that, hey, if a sub m is ever equal to 2 to the any power, then eventually this will get to 1, and you can actually quantify when it goes to 1, right, in terms of log 2. But yeah, so you can kind of see some of these type things that could be used to prove it popping up here. But this is the basic idea of the statement, is that eventually a 1 appears. And you can see in all of these cases there is a 1. One of the times took 8 to get to, but it eventually happened. Okay. So yeah, in each case there is an m such that that's equal to 1. And if you can manage to give a full proof of this theorem before I send out the weekly email on Friday, so if you can prove this for any integer n, so you can't just try a bunch of values and plug it in, your proof has to work for all integers n, no matter what they are, then I'll give you 5% extra credit on the final. Okay, so if you manage to do this, the 5% would just be the minimum grade, or whatever your mark is on the final. I add 5% into it with a cap of 100%, because anyways, but here, please do not spend a significant amount of time on the problem. This is a very tricky problem to prove, and I really don't think any of you will be able to prove it, but I do want you to spend a little bit of time on it. So if you manage to find a proof, and maybe the 30 minutes you spend working on this, because if you spend more than 30 minutes on it, I'll feel guilty, but if you do manage to find something that works for all of them, then I'll give you extra credit. So just take a peek at it, see if you can see anything obvious, and yeah. And here is our meme. There exists some number x such that this is true. Oh yes, somewhere out there it exists, and we must find it and destroy it. Grab your sword, students, we ride. I'm in the wrong math class. I'm finally in the right one. Okay, good old XKCD. But yeah, so I wish you all a good weekend, and I will send out a thing on Friday, probably around noon, but time is not guaranteed, but I'll send a thing on Friday with some comments about this example here, and feel free to type anything in Piazza that you want. When working on this problem, you can type anything that you find. You can fully work with each other to try to solve this problem. You're just not allowed to use the internet. Okay, so I wish you the best of luck, and I'll talk to you later.